So, okay, there is another aspect. And let's talk about turbidity curves. And it's about the density effect that suspended sediment particles have. You have a mixture of seawater or water and sediments, and sediment particles have a higher density. Okay? It's more, sediment particles are more than 2 times denser compared to a water particle. So now if you have a mixture, the sediments actually make the mixture heavier compared to pure seawater. And what they can do, what this can do, this addition of heaviness, of density, can create currents. And currents created by the addition of suspended sediment are called turbidity currents. And the turbidity currents also can create bad shear stress and the turbulence to keep sediments in suspension. Okay? And so now that you get an idea of, well, it doesn't happen all the time, you need a certain amount of sediment. Okay? I just want to show you the effect that you get if you have a certain amount of sediments. And it's a simple mixing equation that you can use here to estimate what is the density of the mixture for a certain concentration of sediment. Okay? And there's a little table where it tells you for a certain concentration of sediment in kilograms per cubic meter, what is the density increase that you get. Okay? And what you really need to know is that you only get a noticeable changes once the concentration exceeds 0.1 of a kilogram per cubic meter. So if you have, once you have more than 100 grams per cubic meter, you can have effect. Okay? So only if you have a big addition of suspended sediment, like you have after a big storm event, then you can have a turbidity. Okay, and I just want to show you one example, and it's just an example derived from a computer-based model. Okay, you can search for examples. There are examples of observations in the literature, but I just decided I want to just show you an example of a highly idealized example. And what's shown here is something that we call a submarine canyon. And you can see a shelf which is 100 meters steep, and then you have a shelf break and it gets steeper, and the maximum depth in this example is only 1,000 meters. Okay? Just an example. You can see the canyon, and the event is triggered by a transient source of suspended sediment along the shelf. So you assume that there is a storm event and that you always have suspended sediment there. Let's see what happens. And now I show you the predictions. It's not a movie, it's just a snapshot. Okay? And you look from above. Okay? And all you see here is near the seafloor, say 1 meter above the seafloor, the concentration of sediment. Okay? And you also see the trace, the sediment that ends up on the seafloor. Okay, you can see after day 2, there is this red thing here is a turbidity current, elevated levels of sediment. And day 4, you can see it flows down on the right-hand side of this canyon. It moves to the right, and at day 8, you can see the deposition area. The deposition area is this black area here. Okay, you can also see some other features here, deposition area. And this is a typical feature, these deposition areas. Okay, there are now the effects that stay for a long time, the deposition area. And they are well reported. I can ask you the question, why is it here on the right side compared to the axis of the canyon? And the answer is it's because of the Coriolis force, and this is in the northern hemisphere. In the northern hemisphere, the deposition areas are moved. Okay, you might call it downstream, because this turbidity current turns to the right because of the Coriolis force. Okay, so now I also need to add that these turbidity currents are important sources of dissolved oxygen and nutrients for the deep sea organism. Okay, so they also play a role in marine food chains. So and we're really talking about the coastal ocean again here, not estuaries. Okay, so this is a feature of the coastal ocean continental margins called turbidity current.